Hello and welcome everyone. So my name is Niklas and I'm here together with Ole and Korbinian to present novel sources of tunable laser light for quantum center spectroscopy. To be very precise, we will discuss widely tunable continuous wave OPOs, optical parametric oscillators. And here is the outline. So we'll start with fundamentals first about tunable lasers and OPOs, and afterwards the most fun part starts when we go over to the lab to look at how these devices look in real world. Afterwards we'll come back here to look at application examples of spectroscopy of quantum centers. So first we start with a quick look on conventional lasers. What you see here is the laser principle, which relies on creating a population inversion between two states that allow for light amplification by stimulated emission. In the practical realization, conventional lasers need a pump source, which can be incoherent light or current, a suitable gain medium with some form of optical resonator to achieve lasing threshold. For a tunable laser, one needs to find a gain medium with a suitable level structure. So this slide shows an overview of the wavelength of commercially available lasers and gain media. On the top are laser types with distinct laser lines. In the bottom are lasers that can emit in a wavelength range. At first glance, this looks really crowded, but let's have a closer look on tunable lasers. So we skip the distinct lines and then we look at the visible. And if we zoom in, you can see that there are actually not that many choices of gain media in this range. So there's a handful of semiconductor lasers covering certain wavelengths, but with rather limited tunability and the so-called green gap between roughly 530 and 630 nanometers. There are dye lasers, which basically cover almost the entire range, however, not with a single dye. So this can be inconvenient if you want to have wide tunability. Lasers based on Ti-sapphire technology crystals essentially will cover the red, 700 nanometers and longer, and the blue frequency doubled, so 350 to 500 nanometer in the visible. For coverage in between, so 500 to 700 nanometer, one needs to employ a frequency mixing with an additional pump laser. So this can become a really big and cumbersome setup. So on the one hand, for wide tunability across the visible range, choices of conventional lasers are quite limited. On the other hand, many applications in experimental quantum research really would benefit from that. So here's the idea. We use an alternative approach to convert readily available single frequency laser light into the visible using parametric conversion. Notably, the idea is not super new, and optical parametric conversion has been experimentally demonstrated more than half a century ago. However, only recently the availability of high-performance lasers and crystals allowed to realize commercial and practicable device designs. So for a better understanding of the technology and its limitations, let's first look at the fundamentals. Simply speaking, optical parametric conversion is splitting one photon into two photons with lower energy. This splitting is frequently referred to as three-wave mixing of a pump, signal, and idler wave. It is subject to conservation of photon energy and momentum, but otherwise, at least in theory, not subject to other limitations. For the practical realization, OPOs require a pump source of coherent light. They also require a suitable so-called nonlinear medium with preferably strong second-order nonlinearity. The design concept of the optical resonator is to circulate the signal idler, or both through the nonlinear crystal in multiple paths, typically in a so-called bow tie cavity. At the output of such cavities, usually there will be pump light, signal, and/or idler. So a few more words about energy and momentum conservation. First, from energy conservation, it follows that any signal and idler frequency is always lower than the pump frequency. Or, the other way around, any new wavelength will be longer than the original pump wavelength. This has some immediate implications. In particular, generating wavelength in the visible with the OPO would require a pump source in the UV. Second, signal and idler wavelength are dependent. So once a particular signal wavelength is chosen, the idler wavelength is determined as well, and vice versa. As to conservation of momentum, simply speaking, due to the effect of chromatic dispersion, the pump signal and idler waves tend to run out of phase inside the nonlinear crystal. This is unwanted, and phase mismatch should be close to zero in order to obtain efficient nonlinear amplification. The modern solution to this is the so-called technique of quasi-phase matching. Going into details is beyond the scope of this talk. However, the idea is employing a material with spatially modulated nonlinear properties instead of a homogeneous nonlinear crystal. The trick is to allow for a certain phase mismatch over some propagation distance, but to reverse the nonlinear interaction at points where the conversion would go the wrong way. As a result, phase matching allows to design and shift the wavelength range in which conversion is made favorable, and thus optimizing and tuning the gain profile of the nonlinear amplification. So keeping all this in mind, let's turn to the more practical or technical aspects in building continuous wave OPOs. First, while in principle it is possible to keep the OPO cavity resonant on signal and idler, in practical implementations, one usually refers to so-called singly resonant designs. This means that one of the signal or idler wave is circulated resonantly while the other is extracted. It sounds like a detail, but note that for doing so, the output coupling elements needs to be highly transmissive for one and highly reflective for the other. This implies a certain minimum wavelength separation of signal and idler in practice. So in the example here, we circulate the idler and extract the signal. To give you a real-world wavelength example, when pumping with 532 nanometer, the idler can be somewhere in the range 1080 to 1030 nanometer to 1300 nanometer, while the signal will be in the 900 to 1050 nanometer range. Secondly, to ensure resonant conditions, the cavity length needs to be actively stabilized to a multiple integer of the resonant wavelength. This can be accomplished by employing stabilization schemes like Pond-River Hall or side of French, and a piezo element underneath one of the cavity mirrors. For mode selection to ensure single mode operation, mode selective elements are introduced like etalons. As mentioned before, we must keep in mind that for conversion of the output into the visible range, another frequency conversion step will be necessary. We will get back to that soon, but on the next slide, let's focus first on how these elements introduced here on this slide can be employed for different wavelength tuning schemes. So first, tuning over the entire wavelength range or coarse tuning is accomplished by automated selection of optics and crystal temperature, so adjusting phase matching condition. The typical resolution is on the order of 1 nanometer, and wavelength changes require between 30 seconds and a few minutes because of the temperature tuning, which is a little bit slower than other schemes. Stepwise tuning can be accomplished by movement of the intracavity atelon. Typically, the tuning is on the tuning range is on the order of 100 gigahertz, with step sizes of a few gigahertz and a speed of about 1 second per step. Finally, truly continuous tuning or mode hop-free tuning can be accomplished by piezo scanning the OPO cavity length. The tuning intervals are on the order of 10 to 50 gigahertz with a tuning speed of approximately 10 gigahertz per second and a resolution well below 1 megahertz. Now, having a fully tunable OPO cavity at hand, we can finally move to conversion into the visible. So we start with separating the remaining pump and splitting off a part of the primary OPO output. Now we can use the OPO signal to feed a second bow tie cavity designed for resonant frequency doubling or second harmonic generation. Simply speaking, in some sense, this is the reverse process of parametric conversion, as we take 2 photons of lower energy and bring them together to 1 photon with higher energy. So this way, we convert the OPO signal output to wavelength in the visible. Of course, instead of circulating the OPO idler, we can choose to circulate the OPO signal and use the idler part for frequency doubling. This is shown here, and the available OPO output in this range is 1080 to 1300 nanometer, and that's 540 to 650 nanometer after frequency doubling. So in total, with this design, we end up with a wavelength coverage of 450 to 650 nanometer with a small gap around 532. This is almost the entire visible range. Before moving on into the lab, I want to give you an overview of the OPO system that we will look at there. What you see here is the design of our latest addition to the C-Wave series of tunable continuous wave lasers. It goes by the name C-Wave GTR, which derives from the wavelength coverage, which is green to red. It might look a little bit overwhelming, but let me guide you through it step by step. So we start with a pump laser and pick off a small part for power monitoring, creating signal and idler in the first cavity, extracting idler and the remaining pump light, extracting signal, guide it, use a second cavity for conversion into the visible using second harmonic generation, extract the visible output, extract the signal, and add some active frequency stabilization scheme. And now if we employ a 780 nanometer pump laser, we end up with an OPO coverage from 1 to 3.5 micrometer, so almost the entire near infrared wavelength range. And the highlight is, when we convert this to the visible, we have a coverage between 500 to 750 nanometer without a gap. The power levels reached with signal, idler, and SHG are on the watt level. So now let's go over to the laser lab where my colleagues Ole and Korbinian are waiting to show you this device in real world.
Welcome to the HÜBNER Photonics Laser Lab in Hens. My name is Ole Peters. I'm the application engineer for our OPO systems, and together with our product manager, Korbinian Hens, I want to show you the C-Wave GTR system in operation.
Thank you, Ole. I would like to show you our graphical user interface to control the C-Wave laser. It's a web-based interface, so you just use any web browser that you like and type the IP address of the C-Wave and confirm with enter to see this web page, which is controlling the C-Wave. The most important part for a tunable laser is the wavelength selection tab, which is shown on the upper left corner of our graphical user interface. And here you see that you can enter either the signal, the idler, or the frequency double signal, the SHG wavelength. You can type any of those, and the others are calculated then automatically. So let's, for example, say we want to go to a signal wavelength of 1165 nanometers. I confirm with enter, and you see this results in an SHG wavelength of approximately 582.5 nanometers. And by pressing the dial wavelength button, the wavelength approach is initiated. So down here in the wavelength control tab, we see the status of our automatic wavelength approach that we are currently running. So on one hand side, the OPO cavity status, and on the right hand side, we have the SHG cavity status. Firstly, the optomechanical configuration in the OPO is chosen. So the right polling period of the crystal that we are using to approach this wavelength, it's chosen from a lookup table. Also, the crystal temperature of the OPO crystal is chosen. And then, of course, we need pump input. If all that is given, the LEO filter and the echelon are being optimized. And last but not least, the cavity length of the OPO is being locked. Once this process is completed, the SHG process starts. And it follows a very similar routine. So first of all, the optomechanical configuration was chosen by lookup table values. Then the OPO was checked if it is already there to be converted into the SHG output. And finally, we do here a crystal temperature scan of the SHG crystal, which happens, it's approximately covering a range of 20 degrees centigrade to find the temperature where conversion efficiency is maximized. If you like to follow these processes in more detail, you can choose here the scans on the menu on the left-hand side to really see what is going on in the system. So we see here the temperature scan versus the photodiode value or the photodiode output from the SHG photodiode. Once the optimum temperature for the SHG crystal is found, the last step, the SHG cavity length is locked, and we can see here in the wavelength control tab of our graphical user interface some buttons for fine-tuning and optimizations. So let's have a look at the output power in the visible wavelength range. Therefore, I use my safety goggles. Let's open the output shutter of the visible output of the SHG by clicking here open. And if we have a look at the power meter reading, we see that we have watt level output in the visible at a wavelength of approximately 583 nanometers. If we close that shutter again and have a look at the signal where we set up the signal of the OPO, where we set up our second power meter and check for this power meter, we see that we have approximately only like 200 milliwatts of infrared power left when most of it is being converted into the SHG. If the SHG would be disabled, this power level would also be typically in the range between 1 and 1.5 watt of infrared power of the OPO signal. We also set up a wavelength meter. And if we have a look at the window here on the right-hand side, this gives us on the bottom right the wavelength that is measured, the wavelength of the OPO signal. So you remember here on the top left of our graphical user interface that our set point was 1165 nanometers, and you see that we approached that quite closely just by lookup table values. The specified accuracy of that lookup table value approach without any wave meter feedback, just based on this lookup table values, is plus minus 2 nanometers in the infrared wavelength range, resulting in the visible output and an accuracy better than plus minus 1 nanometer. We also have the opportunity to fine-tune our laser, and therefore we have a look here at the frequency that is measured from the wavelength meter of our laser. So this is really a live graph showing the frequency of the laser, and we have different tuning mechanisms. So we have the discrete steps that we can do with the echelon as a first thingy, and by just stepping up and down with these arrows in a certain step size that is chosen over here, we can change the frequency of the laser. And you see the result on the bottom right-hand side in this wave meter live measurement. So pretty much immediately, we have a change of a few gigahertz, approximately 6 gigahertz in this step. These steps can be small as like 2 to 3 gigahertz in the infrared, resulting in 4 to 5 to 6 gigahertz in the visible wavelength range. Despite stepping the wavelength, you can also continuously tune the laser over a range of a few gigahertz by enabling the continuous tuning of the OPO cavity length. So pressing here this enable button, we initiate that motor-free scan around the center wavelength where we start from. And we see here that we apply a triangular shape for scanning at a rate of 0.1 Hertz.
All right. Wonderful. Thank you, Korbinian and Ole, for sharing these information. So let's move on with some application examples about how these widely tunable optical parametric oscillators can be employed in experimental quantum research. So I guess that many of you are well familiar with photoluminescence excitation spectroscopy, but let me give a brief introduction to those of you who aren't. The challenge with a single quantum centers is that in most cases, it is impossible to measure the absorption cross-section directly. The way around that can be photoluminescence, where you excite the sample at different wavelengths and measure the photoluminescence signal with a really sensitive single photon detector. If you don't pump the color center into a dark state, that gives you a good idea about the absorption cross-section, which is a vital part for characterization of the quantum center. Here's an example. This method is used by the groups of Alexander Kubanek and Fedor Yelecko at University of Ulm. They recorded the spectrum of ensembles of silicon vacancy centers in diamond at 2 excitation energies. You can see that there's only one big absorption feature centered around 540 nanometer with a width of about 100 nanometer. By increasing the pump power, one obtains about twice as much photoluminescence signal, so the measurement is not saturated. They also repeated the measurement with germanium vacancy centers in diamond and observed this structure with a clear feature at 604 nanometer, which is associated with a zero phonon line. This work helped understand the energy level structure of these two important color centers in diamond. Now, let's focus on the structure of the zero phonon line of germanium. In this work here, we looked at an ensemble of germanium vacancy centers, and now we look at individual germanium centers at low temperatures. So this work has been done by the group of Weibo Gao at Nanyang Technology Institute in Singapore. So cooling down the centers freezes out the inhomogeneous broadening and the phonons. When you look at this, you can do fine-tuning by motor-free scanning the OPO output and looking at the photoluminescence emission signal. When you and here you can see the fine level structure, which refers to the fine structure spin orbit coupling of the different levels of the germanium vacancy center. Another interesting finding is that if you only use the resonant laser beam, then these absorption bands disappear, the centers go into a dark state. You can switch them back on by using a gating laser around 532 nanometer, and while the gating laser is on, the absorption line can be detected. To summarize, OPOs became practical tools to generate widely tunable laser light with a variety of really attractive characteristics, like high output power, narrow line width, extremely high spectral purity, especially compared to other tunable lasers, high pointing stability, and so on. We demonstrated OPOs covering the visible range from 450 in the blue to 3.5 micrometer in the near infrared. But however, the OPO concept is not limited to this range. It is rather a question of design. So taking all this together, OPOs can be a really beautiful and powerful tool. And with this, I would like to conclude and thank you for joining.
Thank you very much, Niklas. And thank you everyone in the audience for your attention. Thanks for your questions and comments also. If you haven't done that already, you can type your questions and comments into the chat box on your screen. And thanks for joining us for Novel Sources of Tunable Laser Light for Quantum Center Spectroscopy. This is part of the Photonics Spectra Conference hosted by Photonics Media. And you've just heard from Dr. Niklas Waasem and Korbinian Hens. Thank you so much.